So exponential numbers, as explained before, are a way to deal with very, very large numbers or very, very small numbers. On the board here, I have a range of numbers which range from very, very big down to very, very small. And you can see how we use scientific notation to be able to summarise these numbers in a way which is communicated quite clearly. So if we have a look at, say, the number 10, you may know that that's represented obviously by 1 times 10, 10 to the 1, 100, 10 to the 2, 1,000, 10 to the 3. Where 3 here represents how many times 10 you need to multiply the number together. We call these numbers exponential numbers or expressing numbers using scientific notation. In a lot of biology, we are looking at things which are very, very small. And we often use exponential numbers with negative signs up here. So remember, as the numbers here become larger, the overall number that's being represented by the exponential number is becoming very, very small. So you can see here, as the numbers get smaller, these negative numbers here increase. So don't get that confused. I've seen that happen quite a lot with students. So exponential numbers are really, really important. We also simplify exponential numbers even further in biology by using units. And you can see here, if we look at the unit of a gram, which is weight, you see that when we go down in orders of magnitude of exponential numbers by 3, we start going through these very common units which you come across in biology. So you see, when we are talking about 10 to the minus 3 of a gram, we're talking about a milligram. When we're talking about 10 to the minus 6 of a gram, we're talking about a microgram. 10 to the minus 9 of a gram, you're talking about a nanogram. So it's really, really important that you get your head around this series of units and what it means in terms of the exponential numbers as you start moving between them. But you also get a feel for what these things actually really mean in terms of real life. For instance, in the laboratory, and probably you know from cooking, it's quite easy to weigh out a gram. You may have to weigh out 20 grams of butter to cook a cake, for instance. We have balances in the laboratory that allow us to weigh out milligrams. However, when we start getting down to weighing out these sorts of quantities, it becomes very, very difficult. And it becomes very difficult within the accuracy of the balances we have in laboratories to measure out these sorts of values down here. So when you're thinking about units and scientific notation, start thinking about what it actually means in real terms, in terms of the quantities that these numbers are actually representing. So the example we're going to go through today shows how you can use exponential numbers to simplify very, very large numbers. So the example I'm going to talk about is working out how many base pairs are in the cells of an entire organism. In our model organism, we have 20 trillion cells in the entire organism. Now, a trillion is 10 to the 12. So if we have 20 trillion cells in an organism, it means we have that many cells, which equals 10 to the 12 times 2 times 10 to the 1, which in terms of scientific notation, because we add those two together, is 10 to the 13 cells. So in our organism, we have 20 trillion cells, which, if we express this using scientific notation, means 2 times 10 to the 3 cells. Now, we are told from our question, the information in our question, that a cell contains 3 million base pairs. And in terms of scientific notation, a million is 10 to the 6. probably already know that already. So to work out how many base pairs of DNA is in the entire organism, we have 3 million base pairs per cell times the number of cells, which we've worked out here is 2 times 10 to the 13. And using scientific notation, well, we say 3 times 2 is 6. 6 times 10, 6 times 10 to the 19 base pairs of DNA per organism. So you can see how that calculation becomes quite simple when we use scientific notation to do the actual calculation.